lecturer is Don Lincoln. Dr. Lincoln is a senior scientist at Fermi National Accelerator Laboratory. He is also a guest professor of high-energy physics at the University of Notre Dame. Dr. Lincoln received his PhD in experimental particle physics from Rice University. His most noteworthy scientific accomplishments include being part of the teams that discovered the top quark and confirmed Higgs boson. The author of 4 books and many magazine articles, Dr. Lincoln has given hundreds of lectures on 4 continents and to a broad range of audiences. Lecture 1. 2 prototype theories of everything.
Dream no small dreams, for they have no power to move the hearts of men. This quote by Johann Wolfgang von Goethe is still powerful to me, 2 centuries after we first wrote it down. It doesn't matter whether you're trying to broker an international peace treaty, or cure disease, or change a society. It's not the incremental improvements that stir the blood. It's the big ideas. In science, humanity has had great success over the centuries. Isaac Newton's amazing ideas about gravity were the first major scientific steps towards a theory of everything, ideas that we still use to guide our space probes to distant targets, like when the New Horizons spacecraft goes by Pluto. Our mastery of the atom made chemistry possible, and also allowed us to build electronics and computers that can calculate faster than human imagination. Each of these achievements is big in its own way, but they aren't the biggest possible. While there's no denying that these ideas originated from a grand dream, each represents merely a single facet of human knowledge. The ultimate goal of science is much bigger. The ultimate goal of science is nothing less than an understanding of the fundamental rules of the universe itself. That's a pretty ambitious goal when it depends crucially on the idea, which seems to be a fact, that all of the phenomena we see around us are interconnected and arise from even deeper causes. There's a class of scientists who keep asking why, and each answer resulting in yet another question. An example of this might be like asking why the sky is blue, the answer for which is the size of air molecules. Asking why air molecules are the size they are leads to the size of atoms in those molecules and the strength and the nature of the forces that hold them together. The next obvious question would be why atoms have the sizes that they do, and that's because of the laws of quantum mechanics and the properties of protons, neutrons, and electrons. We do that over and over and over again, and the hope is that one day there will be no more questions because we understand the reasons for everything. I did say that we dream big, so let's get down to business. While big ideas are where a final theory will originate, we won't know that we've succeeded until we've rigorously tested it against measurements. That's because details are important in science. Every theory and every observation need to fit together perfectly because all it takes to kill a theory is a single confirmed disagreement between measurement and prediction. To get a feel for what that means, we first must understand existing theories and the rigor with which they've been tested. Ironically, to successfully dream big, we need details. But disconnected details are meaningless unless we understand the bigger picture. Without an understanding of the bigger picture and how things fit together, details can seem like just a whirlwind of disconnected facts. So that's where we'll start, by getting an overview of current thought. Just what are our current prototype theories of everything? Over the centuries, scientists have combined their thinking and observations and distilled them into 2 distinct theories. The first is Einstein's theory of general relativity, which is our best description of how gravity works. Like Newton's earlier theory of gravity, general relativity covers everything from what you see when you drop a ball to the stately motion of a swarm of galaxies. But it also includes things like black holes, gravitational waves, and the nature of space-time. That's gravity. The second theory is called the Standard Model of Particle Physics, and it covers everything else, from atoms and chemistry to light, radiation, and far, far more. So let's talk about each of those theories in turn. Let's start with the Standard Model. The Standard Model explains everything except gravity. Why does a soda fizz? That's the Standard Model. Why does the sun burn? The standard model. The screech of fingernails across the chalkboard? The standard, well, you get the idea. So, if I ask you to start explaining why things work the way they do, you might begin with the weather, the earth under you, or maybe the cycle of life, which means that perhaps you'd start with the scientific fields of meteorology, geology, or biology. But no matter your starting point, if I asked you a few